Mm, Okay, guys. Hello, good morning, everyone. Thank you very much for joining us today in this seminar. And it is my pleasure to introduce Wietze Herreman. I will briefly describe his CV. Wietze got his civil engineering degree in physics in Belgium in 2004. His PhD in mechanics and energetics in Marseille, France in 2009. And he actually works as an associate professor at the University Saclay in France from 2010 to the present. And today he will speak about metal path roll instability, cylindrical reduction cells, and liquid metal batteries. Wietze, thank you very much for accepting the invitation, and please go ahead.
Thank you very much for inviting me. It's my pleasure. It's my second talk of the day. For those who weren't there before, I'm a bit tired because making two talks presentations in one night is a bit too much. So I've put my timer, so I will certainly stop at the right moment, and then we will skip to questions or whatever. So let me share my screen. Voila. So everybody can probably see this. So this is a joint work with Caroline Nore from Université Paris-Saclay, and also a bright student. It's Ladislas Virchalek. Last year, I had the chance to hire this Master 1 student who hadn't found an internship because due to COVID, he couldn't go to Denmark, but I was very happy to hire him. Because together with him, we were succeeded to do part of the work on 3-layer stability theory for these batteries. And well, so our long-term collaborators for the numerics are Jean-Luc Guermont, who's at Texas A&M, and Loïc Capenara, who was a previous PhD student. And of course, this work includes collaborations with Norbert, Gerrit Horstman, and Tom Weyer. So I think that I don't really have to explain what liquid metal batteries are for you, because this is a liquid metal battery seminar. But I always start with this type of diagram when I have to explain it to people that haven't any experience in liquid metal batteries. So we are looking at a stratification of 3 liquids. So it's like a B52 cocktail. And the stratification is self-assembling because of the different densities. Now, the big difference is that we are working with metals and with molten salts. So we need to heat them up quite high to temperatures around 400 to 500 degrees Celsius. So what makes this topic interesting is that we can use these earth-abundant materials to make these batteries. And we also hope that they can have a long lifetime because the interfaces between the different layers, they are all liquid, and so they cannot be destroyed. Now, what is also important is that they already exist. So this is a picture that I got from the website of Ambry with Donald Sadoway. It's small batteries for now, but we hope that they come to be large, and that's why we do studies on them. Now, there are some fluid mechanical questions with this system. And the first is, which kind of flows can we get inside these batteries? And are they annoying or helpful? So this is like two topics that we've seen in the literature of the past. The first generation studies were all focusing on trying to avoid too intense flows, because when you have too intense flows, you can have a short circuit, and we don't want that. But a second generation studies on these liquid metal batteries, well, they change the paradigm and say perhaps these flows can be used to increase the efficiency of the battery. And what does that mean? You have to mix the alloy then. So that's a second generation where flows can be helpful. So in our labs, it's not always easy to make these batteries. So we first try to simulate them. And what is particular is that it's a very multi-physical system. You have to combine hydrodynamics with thermal effects. You need to include how the alloy is varying in composition while it's being charged or discharged. There are electrical currents, there are magnetic fields. So you really need to have like a very multi-physical code to be able to say something about these cells. Now, on the other hand, since we're working in academia, we like to theorize systems too. And that's one of the things that I like to do. What can we say with theoretical methods? And then if we zoom out, which information can we get from all that for the engineers that will make them, or probably and hopefully. So there are probably other questions, but that's my little list. And well, as you've seen probably in literature, there are different kinds of flows in liquid metal batteries. So you have, for example, the thermal convection flow. I think this was the first flow to be examined in liquid metal batteries for very good reasons. It's a very hot system. And when you have an electrolyte which has a low conductivity, you can expect to have resistive heating while you're sending strong electrical currents through this cell. So at least in the top layer, you can expect that you will have an unstable convective system, and you will get thermal plumes rising up. And this can also make the other layers move. The Taylor instability was the second instability that was studied, and it's really a magnetohydrodynamical thing. What you have to do is very simple. You just send a current which is strong enough through the system, and this will create a flow through a magnetic hydrodynamical instability. Then we started studying metal pad roll instability because we noticed that the Taylor instability was a bit weak. You need a huge cell for it to become Taylor unstable. But in fact, when you have interfaces with different and fluids with very different conductivities, and of course, always some background magnetic field. Well, if you're going to make a battery, you will have to have wires, and these wires will make magnetic fields. And when you have the combination of all that, you can create the metal pad roll instability. More recently, we went towards electrovortex flows, where due to the shape of the electrodes that bring current to the cell, you get the Lorentz forces, which cannot be compensated by pressure forces alone. And so you have to get a flow, and that's what electrovortex flow is like. And then last but not least, what we saw was that for a long time, we ignored the fact that alloys in the liquid metal batteries could change composition, that they didn't have always the same density everywhere. But as you charge or discharge them, you're displacing mass from one part to another, and you're changing locally the composition of the alloy, and so also its density. You can think it's small, but actually it's very big. It's surprisingly big, and it's perhaps one of the most strong flow forcing mechanisms that we have in liquid metal batteries. So in our group, we studied a bit all of them. But today I'm going to focus on metal pad roll instability. Now, this is my plan. I'm going to give you an overview of our work. So some of you will certainly be already familiar with that. I think it was a good occasion to do that, to try to see everything together. And more certainly too, because the three-layer stability theory, if I start with that alone, well, I will just make everybody very afraid of what I'm actually doing. So, well, I will start with this. I will start with the metal pad roll instability, and I will assume that some of you are not entirely familiar with this phenomenon. So, what is metal pad roll instability? Well, it's a flow phenomenon that is very well known from aluminum reduction cells, where we have not 3 layers of fluid, but 2 layers of fluids. And what is the phenomenon? Well, we can see there's a spontaneous growth of interfacial waves in these reduction cells, and it's a problem for the aluminum industry. It needs to be avoided. So this is a picture of a typical industrial hall where used to produce aluminium, and you see all these similar units, and all these units these are Hall-Héroult cells. So this is one Hall-Héroult cell. Now I'm not an expert of how these things. I don't know exactly how the currents go. But if I look at this, the picture, then I see one line from the side, and I think that that's where current is coming in. So we need a lot of current to electrolyze aluminium from alumina, and this current is coming in like that. It's injected at the top of the cell. It goes through the fluid layers which are inside, and then it returns back, and then it goes to the next cell. And so we have multiple cells like that, all in line inside one factory. Now, if we look at what one reduction cell is, so we are facing temperatures of above 1,000 degrees. This is because you need to melt cryolite, which is actually the dissolvent for the alumina. And you have, this is the molten salt, which is a very thin layer of about 5 centimeters. It's a very bad conductor with respect to aluminium. Aluminium, well, it's going to be created, so the bottom layer will change in thickness. This is a very good conductor. And how are you injecting current? You're using carbon anodes in stacks, and this is going to inject current from above. Now, let's look at the different dimensions. We have heights, fluid layer heights, which are about centimeter high. And then you have lateral extent, which is 4 to 10 meters. So this is gigantic. It's an extremely shallow system. Now, we have the metal pad roll instability. I already said it before. It's related to waves. And what happens is that you actually get in these cells long wavelength waves that grow on the interface. Now, this is not always a problem, but 5 centimeters of cryolite is not so big. And so there is a risk of short circuit. What does this happen? What happens when you have a short circuit is that you get all the current, which is very high, something like 100,000 to 400,000 amps. It's going to be focusing on one of those anode blocks, and so it will burn down. These carbon blocks will just burn down, and when the cell becomes defectious because of that, and you need to change them as a consequence. So this is not very good for the industrial process. That's why people want to avoid this instability. Now, we are interested in the physical origin of these waves. So let us come back to our setup. We have this huge electrical current, and as I said, it's running through the factory on this line. So this line is something carrying currents up to more than 100,000 amps. Well, if you remember your electromagnetism basic course, then you know with the right-hand rule, this is going to create you a magnetic field, which is mainly upward. Of course, it's never going to be exactly upward, but this current line, you can expect that in the system, there will be some induced magnetic field, and it's going to at least have some upward component. So, well, the physical origin of the metal pad roll instability is simple. It's just the Lorentz force, where you have the current density existing in the cells going down that is combining with this ambient magnetic field. And typically this is a few millitesla. So it's not big, but it's more than 10 times the Earth magnetic field. So this is the situation that we have. And as a result, we can understand quite clearly why we have instability in this system. So let's idealize this entire system. We have an equilibrium cell, no flow, a flat interface, perfectly homogeneous current density. This would be like a base state. So current is going down because you're reducing. And now imagine that you have a wave. What happens? Well, the cryolite is a very bad conductor. So the current will immediately reorganize and will increase, the current density will increase in the parts that are shallower in the cryolite. So this is suggested here by these smaller and thicker arrows. And now this is the total current, the initially imposed plus a current perturbation, small j. If I focus on small j, I will reinforce to the right and reduce to the left with respect to the base state. So I will have a current excess which follows about this path. So it's mainly horizontal inside the aluminium and mainly vertical inside the cryolite. So if I suppose an external magnetic field which is vertical or has a vertical component, you will have a Lorentz force, which is again J towards B with the right-hand rule. You will get a Lorentz force that will drive the fluid in that direction. So what will happen is simply that the wave will pop up at a new position. You will have a rotated wave position. And from that, everything starts again. So you have a current, perturbation, a magnetic field, a Lorentz force, and it will bump up at the other side. So what do you see in these sketches? This is the Sille mechanism, and it's just the way how a rotating wave can appear in this system. So it appears that a rotating wave, should be chosen. Now, the result is that, but there is a big but there. The but is that it works if the transverse standing waves are coupled. So don't forget, we are in a rectangle. You can have one wave like that. You can have another wave like that. You can have much more other waves. But let's just take one standing wave along X, one standing wave along Y. Well, through the Lorentz forces, they are going to be coupled. The standing wave along X will force a standing wave along Y and vice versa. So this is a typical scenario when you have two waves that couple to each other. We call that a parametric resonance. And to have resonance, you need frequencies of standing waves to be close. So frequencies of the wave along X and frequencies of the wave along Y need to be similar. And this depends on the geometry of the cell. So as a result, instability criteria that you will find in the literature depend on geometry too. And this is the most popular form of the instability criteria. You can have instability when some non-dimensional number beta, which is a ratio of current IB times magnetic field BZ, the difference of density J, and then there are two heights, the fluid layer heights appear there too. So this number, when it's bigger than some critical number that depends on geometry and dissipation, then you can have metal pad roll instability. So this is a criteria that is based on many stability theories, and all of them focus on shallow cells. So that's where some design criteria comes from. If you want to avoid the metal pad roll instability, you can do that by increasing the layer height. Take bigger layers. This will decrease beta, and you can go below probably the instability threshold. But the problem is that, it costs money because the cryolite, if you make it thicker, the resistance will go up and you will have more Joule losses. And we already have 3% of the world's electricity that is lost in producing aluminium. So, that's one reason why this instability was so heavily studied also in academia. People try to understand it very well to define how to recognize how we could avoid it. Now, let's look at the different literature. So there's a huge literature on metal pad roll with two layers. So the earliest work started in the 70s, then it ended about 2000. So there's a more recent paper, but it's quite close to the previous ones. So let's say that stability theory actually, it took 30 years to develop and it stopped in 2000. Now, there were useful nonlinear extensions to that because stability is okay. It allows you to say the cell can become unstable beyond these limits, but you don't know how big your wave is going to become. So these people have taken these shallow models and made out of them nonlinear extensions, trying to give answers to how big a wave would become. So this is a bit after. And at the same time, when bigger computers were starting to be there, people started to do multi-phase numerical simulations. So these are very early works like by Vinko Potočnik. This is really like the pioneers, but at the time, the numerical resources were not those of today. We all know that. And so it's normal to see that if you look at the years where these simulations appeared, Well, it's recent because you need big computers for that. So it starts in 2003 and then it still continues today. But there's a time gap between stability theory and 3D simulations. Now, when you have big money, you can do experiments. And so the thing is that metal pad roll instability, mainly just as most MHD related stuff, there are not so much experiments because, well, liquid metals, most metals, they melt at high temperature. You already have to use some particular metals like gallium or like gallium or mercury if you're not afraid of that. But we don't have a lot of experiments. So we have the recent experiments by Pechenko, which use one fluid and some needle array to mimic the situation of having one fluid which is a good conductor and another one which is a bad conductor, but the other one is just not a fluid. So we don't have a lot of experiments. Now, what about metal pad roll in liquid metal batteries? 3 layers. Well, if you see, if you know all this, and I think that even the people that haven't heard about metal pad roll instability before this moment, you probably understood a bit how this instability is coming along inside cells. So what do you need? You mainly need some kind of perturbed current loop. Dancing interfaces will do that. So the 2-layer situation that I earlier sketched, well, you can just have about the same thing in 3 layers. You will have a Lorentz force, which is going to act in opposite directions towards you on the top in this panel, away from me in the bottom, but there's a Lorentz force. So that means that you can probably have just the same thing. But the question is it always destabilizing? And that's not so sure. I will come back to that a little bit later. So now, what is the literature on metal pad roll instability has been advanced since 2015. So we have all these articles. So it first started with Zikhanov, who extended a solid slab model of Davidson-Lindsay to do 2 slabs, saying, well, we can do perhaps the same type of instability in liquid metal batteries, but it was not yet a battery. And then we saw a whole bunch of people that previously worked on aluminum reduction cells. So this is, for example, Valdis Bojarevics, which is student Andrzej Dux, Sergei Molokov, Zikhanov, also Oleg. So all these people have worked on shallow models of Hall-Héroult cells. So they just put an extra layer in their system, and it was a bit of work to get there, but all these models already exist. So on the other hand, this is where you see also the group of Dresden coming in. Nore did the first simulations, 3D simulations of cylindrical magnesium antimony liquid metal batteries. And this was followed after with Gerrit that did 3D simulations of cylindrical LMBs and discovered the importance of having coupled wave regimes in there. Now, what do you observe? We participated in the studies of Norbert, but it was mainly Norbert's work, but we come later. Voila, we are not at the front of this topic, but I think that we have something to tell. So this brings me to my to the 2-layer stability theory that I have for cylindrical LMBs. Now, what is the timeline and the motivation here? So in 2014, when we started the PhD of Loïc Capanara, and his project was in part to extend monophase MHD solver, Svimans, which we have been developing since a long, long while, into a multi-phase MHD solver. So you go from 1 liquid to 3 or 2 liquids. We do that using a phase field method. So Svimans is a very big code, and we can do any type of axisymmetric fluid domain with it. It was designed to do dynamo problems, but we decided to do some more applied MHD problems. And so this is why it was changed a bit. In terms of liquid metal batteries, this means that we cannot do rectangular cells. We can only simulate cylindrical cells, but we can then reach sometimes very high precision using that solver. Now, in collaboration with Norbert Weber, Norbert came to us. I don't know exactly if it was 2016 or beginning 2017, but we started a collaboration with Norbert and we said, okay, let's try to do a benchmark. You have your code, OpenFOAM. We have ours, which is Vimans. We are not really so sure about everything in there. Let's try to do a benchmark and make a physical test case for our codes. So this was a very interesting project because we found bugs in both codes. This allowed this example. It was really difficult, like to make things match, but we succeeded. So in the beginning, we tried to reproduce the few works that were available on metal pad roll instability in cylinders. This is the work by Gerbeau, but we could not reproduce their results. So this is like a snapshot from their simulations. Obviously, there are things which are very good, but I think that everybody can see this is a very rough grid. And now I think that I'm pretty sure that this is not enough to do metal pad roll instability in even very tiny cells. Now, we found another example, which is the work by Steiner. Steiner was a PhD student from a Swiss group that has been working since a very long time on aluminium reduction cells. And we succeeded to reproduce that using both our codes. Now, this is the work, a snapshot from the work from Norbert, who did in 2017 2 papers on metal pad roll in magnesium antimony cells. And he found this rotating wave and he did all kinds of simulations. So first of all, he confirmed that metal pad roll was possible in 3D DNS simulations of magnesium antimony. Sorry, it's not SN, it's SB. He also did a very big parametric study in which he varied current density, imposed magnetic field, density of the layers, viscosity of the layers, height of the layers, everything was varied. He showed that you can have a strong enough wave to create a pinch. Well, but my observation there was that there was no theory to compare with quantitatively. We had nothing to compare with. We could just say, okay, we have this criteria on beta. Do they apply? Well, we don't know. It's 2 layers or 3 layers. In fact, what was most important is that the most existing stability theories for metal pad roll-in theory, they were designed for these huge reduction cells, and they ignored dissipation. Why? Simply because dissipation is difficult. You need to find how flow is going to be dissipated in thin boundary layers, and that can appear everywhere. It's not so simple to capture that. So most stability theories, they just put that away and ignore dissipation. They are also all shallow, or practically all shallow, for very good reasons. You have seen that the Hall-Héroult cells that were intended to study, they are shallow. So I really understand these choices. But the thing is, when you do simulations, you always have to put some value of viscosity. You cannot do dissipation-less simulations. So we don't have anything to compare with. And this was my main motivation. This is when I started to be really interested. Can we propose a quantitative stability model for metal pad roll inside these cells? Now, this has led to 2 papers on 2-layer. This is a 2019 paper in JFM, and last year a paper with Caroline in Physical Review Letters. Now, let me just look at my time to see where I stand. Okay, I'm consuming a lot of time in my introduction. The instability mechanism in a cylindrical version. So cylindrical cells don't exist, but they are academically interesting. Why? Because the rotating waves are simpler. So if you look at what the rotating wave flow, the one that you drive with metal pad roll instability, it looks just like that. So you have here a function which depends on theta and omega mt, which is actually something that is rotating at a rotation speed of minus omega sur m. So if we look from above, this is the situation. You have here a positively rotating wave is one which is going to have omega over m smaller than 0. In rectangular cells, metal pad roll instability couples at least 2 transverse waves. In cylindrical cells, metal pad roll instability, it's just one wave that can amplify itself. And that's why it's interesting to study also metal pad roll instability in cylindrical cells. It's one wave that is amplifying itself. So if you look at how this works, look, this is a rotating wave, and the green arrow is going to give you the direction of the instantaneous flow associated with this rotating wave. You just have to imagine how the fluid needs to come towards you to make the wave rotate. So on top, if it rotates in this direction, fluid is coming towards you. In the bottom, fluid is going away from you, and then the wave will rotate. We already know this picture. Due to the conductivity difference, you will have a stronger current in shallower cryolite paths, so it will be reinforced. This creates a small perturbation current loop, and if I evaluate J cross B, now I see that it's aligned with the bottom flow. This means that you have power injection. The flow receives power from the Lorentz force, and this means that it's going to be magnified. This same picture, you can just throw it at any rotated position. Power is always being injected in this way to this rotating wave. So in our theory, this gives the dissipationless growth rate, which you have there. But what about dissipation? I already told it's not so simple. Well, we have here a 2-layer case. Viscous dissipation is going to predominantly occur in Stokes bound layers that are this wide, the square root of nu over omega. And this dissipation occurs near the solid walls, but also near the interfaces. So this is something that people have some misconception about. When you have 2 fluids, you can have boundary layers, dissipative boundary layers near the interface. It's not a surprise, you have a shear there. So you will have boundary layers. In our theory, this is going to appear as the viscous dissipation rate. The magnetic dissipation rate, what is it? It's related to induction by flow. So we have a term in the Ohm's law. When you have a flow and magnetic field, you can have induced currents, and when you have induced currents, you have ohmic losses, and this will create extra dissipation, but only when you have strong enough imposed magnetic fields. So in our theory, this is lambda VV, and it's also expressed in seconds, 1/seconds. Now, let us look at the perturbation theory in a nutshell. What did I assume in that model? So we have a system with 2 layers, arbitrary material properties. The top is going to be, the top plate is in contact with a very good conductor with respect to cryolite. The bottom is supposed to be less conducting than the aluminum. And then I suppose a base state at rest and an initially flat interface. And what I do is I first characterize the gravity waves in this system. So this gives me this dispersion relation that depends on wave numbers, sizes, gravity, interface tension. Then I use a perturbative approach to calculate how these waves can be destabilized by small Lorentz forces. This is my growth rate, lambda V. And then I will also calculate in the same way how viscosity and magnetic fields are going to damp everything. Technically, what do you need to do? You need to find these growing rotating waves. So this is interface elevation, arbitrary amplitude, Bessel functions, azimuthal wave number, frequency, omega, and growth rates. That's the one we want to calculate. So you do this perturbative expansion, supposing that Lorentz and viscosity is small with respect to inertia and pressure. And when you have that, you can actually calculate the growth rate as the sum of 3 independent terms. And we calculate them using solvability conditions. Now, this is very technical and I won't explain it in much detail. But what do you have to know? That all the growth rates that appear, they are ratios of integrals. Like the growth rate, dissipationless, is going to be a ratio of PV over 2K. And what is PV? PV is simply an integral that it represents the injected power from my instability mechanism. So it depends on the spatial structure of the wave flow, and it depends on the spatial structure of the electrical current. K is just the kinetic energy, or the potential energy, it's the same. When you do 2K, it's just mechanical energy. So you have here what our theory is basically some kind of application of the mechanical energy theorem. If you know the injected power and you know the mechanical energy, you can calculate at which rate the things are going to grow. Voilà. So you can evaluate all these integrals and gives these lengthy expressions with all terms, but you can calculate it exactly. And this is really an advantage with respect to rectangular cells, where you always arrive on matrices that couple different waves. Here it's really an explicit thing. Now, I won't show you the growth rates for viscosity, viscous damping, and magnetic damping. Let's look at some results. So this was our first comparison for a small reduction cell of about 3.5 centimeter in radius and 15 centimeters high, with the properties of aluminium and cryolite. So this is a Steiner case. We know that it was unstable. And if we do simulations of that, we observe a rolling motion. So you see this line is the theoretical growth rate. Let me just put my alarm on. Okay. The black line is the theoretical growth rate. The dots represent the numerically measured growth rates in two different codes. So really, this was months of work, and we reached excellent quantitative agreement on this instability. So this was really, for us, for everybody, a big success, because it validated Sveman's approach, it validated open foam approach, and it also validated the theoretical model, which was quantitative. Now, the work by Nore, if you look at this picture, the bottom is undeformed. The bottom interface is almost flat. And this is because this bottom layer is so heavy. Magnesium antimony batteries, they are almost as two-layer cells for what concerns metal pad roll. And this is because the density difference of the top with respect to the salt is weak, with respect to what you have on the 2-3 interface between the salt and the alloy. So this means that you will have very easy deformations of the upper interface and very undeformed interfaces at the bottom. So we can apply this two-layer theory. And if you do that blindly, we actually found the growth rates of Nore. So this is without adjustable parameter. This Nore measured these growth rates, well, 2 years before I tried to apply this theory. So again, this showed that the theory was very precise and had a predictive capability. Now, this brings me to more recent work that we did with Caroline. Can we make a room temperature metal pad roll experiment with two liquid metals? So our stability model is different from others in the sense that we didn't assume anything special about the conductivities of the layers. I can put anything there in sigma 1 and sigma 2. So this factor is absent when you have very huge differences in conductivity. You can easily verify that when sigma -1 is very big, well, this just simplifies to 1 over tangent KH1, for example. It's going to be independent of the conductivity. So that's what all theories assume. Using our theory, we can test whether metal pad roll instability is possible with two liquid metals. So why is that interesting? Well, metal pad roll, you can do it actually probably at room temperature in the lab. Many have thought about this possibility, but nobody has tried. Why is that? Well, simple. No previous stability theory allowed to consider this possibility of having two rather well-conducting metals. All theories assume a very big conductivity jump. So we have tried different combinations, for example, gallium with mercury, gallium with galenston, immiscible and an immiscible case. And let us take out a small cell. So this is not very important. These are the properties of the materials. We found them thanks to Tom Weyer, who gave this very valuable input. And we see that there is a conductivity ratio of 3.8. The question is this enough so that the interface, when it moves, you will get enough current perturbation? We don't know. But we know we can apply the theoretical model. And this is a stability chart, which shows you the growth rate in the JBZ plane. So current with respect to imposed magnetic field, gallium and mercury. So metal pad roll is really not out of reach. You only need a current of 300 amps inside this cell, which is 2 centimeters here, and 20 millitesla. So this is really possible. And especially when comparing to, for example, the values that needed to be used for Taylor instability in the experiment, this is really low. This is possible. So we have done some simulations for magnetic fields using Coates-Feynmans, and this is extremely difficult because the Stokes boundary layers where you have this dissipation, they are so thin. They are 0.08 millimeters wide. So if you have a 2 centimeter cell, you are really facing here a very thin boundary layer with respect to the radius. So we needed to develop a new multi-phase algorithm. This was work done by Loic Capenara. And this is how it looks like. These simulations are really huge, hugely computationally intensive. Like to make this movie, I think that it's really a lot of computational hours. This is so difficult because the Reynolds number is about 10 to the 4th. And as you see, we have a high amplitude turbulent flow. From my perspective, this is the most challenging DNS of metal pad roll instability that we have ever seen. And don't forget, we are in a 2 centimeter cell. So we have, again, quantitative agreement with our theory. And so in this article, we found that this was a very useful message to send out to the community. And so we published this in PRL. We should build this experiment. So with Tom, I made this nice sketch on how we would imagine this. And you can find this on web if you want to design this experiment. I will be happy to collaborate with you. Mm-hmm. Now, let me look at my time. Son dans 5 minutes. This means that I still have to tell you the 3-layer instability in 5 minutes. Well, perhaps I'm going to take 5 extra minutes, but I'm not going to do much more. I promise you. So the 3-layer instability theory, given that we had different successes for this thing, we said, oh, it was always a good idea, right? Can we go and push on this on to 3-layer liquid metal batteries? So my motivation to do that was Gerrit's article, who published this table of different liquid metal batteries with different densities. And as you see, there are different density jumps on the different interfaces. So delta rho 2,3, this is the density difference on layer 2,3, on interface 2,3, and delta rho 1,2 is the density difference on layer 1,2, and we make a ratio of that. So most liquid metal batteries, because they have a heavy alloy per definition on the bottom, they will have a bottom layer which is very heavy. So it will be practically at rest, and the metal pad roll will often be just as in a 2-layer system. But not always. There are some types of more exotic liquid metal batteries where you can have almost equal density jumps on the interfaces. And that's something that Gerrit studied. Now, what did he find? This is a plot of the period of the different waves. And as a function of this ratio of density jumps. And you see that in some parts, you choose like one wave, you're on one branch of frequencies, and on the other, in other parts of parameter space, he found other waves which were more symmetrical. So I thought this was very interesting, but can we explain this wave selection? Why do we have one wave in one part and another one elsewhere? So I just took my theory. It's really the same thing. It's really the same approach, but much more Bessel functions. So this is why I didn't do it anymore. It took me 2 years to really be convinced that I wanted to try it out, because I was a bit at the end of this story. So voila, now we're there. But what is the difference is, well, with 2 interfaces, we have 2 classes of waves. Give me one azimuthal wave number, one radial wave number, and plus or minus sign. Then you calculate a wave number, radial wave number k, the frequencies, and an amplitude ratio, which is in epsilon and mi notations. So you have here two types of waves, fundamental ones, a slow 1-1 minus wave, which is the fundamental sloshing wave. And you see that the interfaces are in phase opposition. So this whole pattern will rotate for this type of wave. A rapid 1-1 plus wave has symmetrical deformations on, and which means that when you have a maximal deformation, it's going to be maximal deformation on both. So this one is always slow. The minus one is always slow. The plus one is always fast. Now, for each of these waves, we can calculate growth rates and dissipation levels exactly in the same way. The whole difference is just that you need to sum power injected power over three layers, and the mechanical energy, well, it involves both interfaces or kinetic energy everywhere. Now, I will share, no, I don't want to share you the formula. They will appear, it's of no use that I show this explicit formula, but we can explicitly calculate everything. And let's look back, for example, at what this theory allows us to do in the simulations of Gerrit. So first of all, in my notations, the 1-1 minus wave, the slow wave is the blue branch, the plus wave is the purple branch. And now, from my theory, I calculate instability thresholds theoretically. So now this is a very complicated chart. The bottom, you already see this density ratio, difference ratio, and on top you see the current, the critical current for the onset of instability. So this data was very absent in Gerrit's article, but when you do simulations, you need to put some value of current. It's there in the text, but we didn't have the data at that point to know for which point we had indeed this current. So Gerrit provided me with this data. And so plus signs or this plus wave in the late time, minus signs or this slow minus wave in the late time. The curves, the blue and the purple curves, they are the stability threshold lines according to my theory. So everything that needs to be above. If I have an unstable simulation, I need to be above that line if I expect an instability of that wave. So what you see, for example, is that you can see that the minus wave, well, the purple branch is below the blue one in most of the parameter space, which means that the minus wave will be the selected one according to theory. But there is a branch crossing which occurs when the blue is lower than the purple one. And then according to theory, well, the plus wave can be more unstable. What you also see is that, well, you need bigger currents to get unstable simulations when you have these density ratios around 1. So I would say, it's not so good, this comparison. Theory is not so perfect. But don't forget, we're looking here at late time simulations, and late time simulations, it's not the same as linear stability. So what we do, well, if you want to compare simulations to theory, well, you need to compare the same thing. So linear stability means growth rate. And in some simulations, we were able to measure that. Here you have two plots of fits differently done in open form or SVIMANS. And when we do that, this is a growth rate charts, numerical, the data points from the codes, and then the theory. Well, on this chart, it looks really good. I would say this is not too bad as an agreement. And what you have there is a weak instability region that is already present everywhere. It seems that in that region, it's difficult to get instability. Why is that? If you look at the growth rate in the same chart without dissipation, you can see that even without dissipation, you have absolutely no instability at very particular points. Why? And this is something that I found interesting. Metal pad roll instability in liquid metal batteries, it's a story of opposing powers. There's a weak instability because power is injected in one layer, but withdrawn possibly in the other layer. So how can we understand that? Look at this chart. This shows you the instantaneous flow that we can have together with this antisymmetrical wave. So it's going to point in the same direction in the top and the bottom. The flow, the current is going to be magnified as before. If we make the same type of plots as in the two-layer problem, what do we see? We find J cross B aligned with the flow on top, so positive power injection in the top, but negative power injection in the bottom. Destabilizing in one part, but stabilizing in the other. This can result in no net amplification. Now, for the other wave, it's just the same, but the waves is different. Your fast wave, we're going to give you a flow that goes in one direction on top, a flow in the other direction in the bottom. The perturbed currents look like that. And so if we make this plot, we're going to be in this situation where we have the same thing. We can have opposing power injection in both sides. So same results. Now, when I make these power density plots exactly, when I calculate these quantities for my waves at the points where I have zero growth rate, this is what I see. You have perfectly symmetrical power density plots. If you sum everything up, it's zero. So you can indeed have, this is a particularity of metal pad roll instability in liquid metal batteries. You can have weak instability because you can destabilizing in one part and stabilizing in the other. And this explains why we have huge instability thresholds. We just don't have any instability there at these points. The system equilibrates itself. Bon, voilà. I think that it's time to wrap up. So let me wrap up with this final plot. Voilà. So if you now have your theory, you can do some predictions on what you will get metal pad roll instability in large, shallow liquid metal batteries. So I took the configuration of Tux and Boujarevich's GFM paper. So you take a very huge rectangular LMB, you make a cylindrical equivalent of that. So you try to do everything the same, which is the same section, the same layer height, the same total current, the same current density. I have to put some viscosity. They do dissipation-less models. And the question is, what is the minimal vertical magnetic field to have an onset of metal pad roll instability? This is like a classical question for metal pad roll instability theory. So they do that. They did that for any different types of cells. And this is the plot that I can produce using my theory. So for all the different types, you can have sometimes for this lithium tellurium exotic cell, you can have a plus wave at threshold. But what you have here is there's no adjustable parameter in this theory. And I estimate that for these cells, you need magnetic fields of around 0.1 to 1 millitesla to have a metal pad roll. So it's certainly present there. And how is this affected, this threshold, by electrolyte thickness? Well, actually, so I have a very precise dissipation model. Not much. If you change the height of the electrolyte, which is a classical trick to prevent instability in Hall-Héroult cells, the thresholds, they should change. Well, they don't change that much. They actually remain quite the same. So here I changed from 5 millimeters to 5 centimeters. It almost remains the same. So thinner electrolytes are more unstable indeed. I checked that without dissipation, but they are also more damped. And this brings me to a point that I would like to make at the end. In most of all these simulations, the metal pad roll is as in the two-layer system. Instability occurs according to this criterion in shallow cells. And we always say we need to increase the layer height because it increases stability. My question is, really? Are we sure about that? I'm not so sure. And because viscous dissipation, ignored in most theory, is essential. So are we sure that we model even these two-layer systems so good? I'm not sure about that. Voilà. So I took more time. Sorry, too much slides. My conclusion is we have done an original metal pad roll theory for 2 and 3 layer systems. It is a perturbative theory, so it's limited in use. You cannot do any kind of parameters, but we can do arbitrary conductivities. It's non-shallow. It has a precise description of viscous and magnetic dissipation, and it really compares well with DNS. So metal pad roll with 2 liquid metals, I showed using this model that it's possible in the lab. Metal pad roll and liquid metal batteries, I learned that it's a story of opposing powers. It's not so easy to see from the other theories, but you can be destabilizing on one side and stabilizing on the other side, and it's all a matter of the right equilibrium. And then, general question that comes out, do we really have it right that thinner electrolytes in Hall-Héroult reduction cells or even liquid metal batteries will decrease instability thresholds? I'm not sure. So please find our work in these articles, and thank you for all the time you've been listening to me. I hope it was interesting enough to you.
Great, excellent. Thank you, Wietze. Very nice presentation. So, and just in time. So perfect. So we have enough time for questions from the audience. So please feel free. Yeah.
I would have one if I may start.
Please go ahead.
Wietze, is this the case that Gerrit looked at in this early paper, where you are in the strongly coupled regime, and you get these 2 counter-rotating vortices? Is this case captured by your theory as well?
What do you mean? The bulge instability.
The tromps, exactly, yes.
No, the bulge instability is different. The bulge instability is a purely axisymmetric instability, and it's actually, in my view, it's a subcritical phenomenon in my view. I can detail that later. I already discussed this with Gerrit, but this is something that completely falls out of my theoretical description. And there's a very clear indication for that, but then you need to look at, for example, have a glimpse at these formula. So if you look at this typical integrals, you have a wave factor, and this wave factor is depending on the azimuthal wave number. If it's 0, no growth. So this theory will never describe bulge instability.
Okay, thanks a lot. Yeah, sorry, I was a bit hastily with the question. Thanks a lot for the great talk. Was excellent. Great overview.
Well, it's your work, Tom, also. So you were very happy to see that. Of course, you say it's very good. When it's your work, I agree.
No, it's not true.
Okay, guys. Professor Boharevich, please go ahead.
Hello. It's very nice to see you after a while.
Hi, Valdi. Yes, true. I agree.
I was following from the middle of your talk about, and
yes.
I noticed at the end you mentioned our paper, and you told there is no dissipation, which is not true. There is no dissipation and also dissipation, and even analytical criterion with dissipation.
Yes, but I was talking about this. Yeah, perhaps I agree, but so this plot that I made is especially for you. This plot I really made for you and Andrzej, because I thought, look, I want them to understand what I do. And the plot that you have in your JFM article is similar. You immediately recognize the same style, I guess. You have the same representation. I used it precisely that for this reason. So what you see is that my thresholds are 2 times as high for these points. It's very comparative, and your thresholds in that plot are dissipationless.
Yeah, but I'm also including dissipation. All practical cases for the circular one should include dissipation. Otherwise, it's absolutely unstable. The same as square cell, square section. Lx and Ly equal, then you have always this rotating wave with infinitesimal BZ magnetic field starting immediately when there is no dissipation. So dissipation is really crucial.
I compared with this case.
Yeah.
So if you have data, the same data with viscosity, I think that the plot was made for this cell.
Okay. So anyway, very nice to see you mentioning us. And
of course,
I can see that you are continuing this research very intensively, doing some things which, to my opinion, are quite unpractical. No real realization. So apparently you are happy to be able. We have no disability to continue in such direction. So we concentrate on practical aluminium cells, which are giving some and practical realization.
Yeah, I know, but that's the difference between France and your situation. We have no time to do research, but we can do whatever we want.
All right. Okay,
voilà.
thank you very much.
I'm happy to meet you in the future soon enough, I hope.
It's difficult now. Even TMS meeting was remote for me, at least.
Well, we will meet soon. Thanks.
Next year, probably. Yes. Yeah. Okay, see you then. Goodbye.
See you. Bye.
Thank you. So, any more questions from the audience? Wietze, at some point you mentioned that in the case of the aluminum cells reductions, this metal path Rayleigh stability will degrade the carbon electrodes. In the case of liquid metal batteries, do you think that this metal path Rayleigh stability will have an effect on the current collectors?
No. First of all, if you talk with some people that are in the electrochemistry area, it's not because that. So what will happen? You can have a short circuit, you can have a pinch of the electrolyte layer, but this is not going to make your cell explode. So everything remains liquid. So what happens is that when you have this short circuit, you just won't have an electron that is going through to the outside circuit. You will have electron and ions exchanging at the same place. You will just have a reaction which is strong between the top layer and the alloy, but voila, it will probably die away. So for the current collectors, well, we don't yet know how they are going to look like. Like in our models, we really make very strong assumptions about them. I don't think that there is any reason to make them from carbon, for example. I think that we can use any sufficiently conducting and material that is possibly heated up to 500 degrees and still remains good is going to be okay. So we don't have the same restrictions. The reason why they use carbon anodes in Hall reduction cells is that you need to also burn down while you need to recover this oxygen from this alumina, and this is going to be consumed as carbon dioxide in the cell. So these electrodes are anyway being consumed in the process, which is not the case for, let's hope it's not the case for liquid metal batteries. Otherwise, if they consume the solid electrodes, then we will not have an interesting technology, I guess.
Okay, yeah. Thank you very much.
Voilà.
More questions from the audience? We still have some time.
May I add something?
Yeah, please go ahead.
I found some old current collectors in the chemical lab, what Steffen used. And there the thing was he had a metal foam made of nickel iron or only nickel, let's say 3 centimeters high, 3 centimeters in diameter. And when he had short circuits, then usually what happened was that the lithium and the bismuth reacted and formed some intermetallic phase. And the intermetallic phase was then connected to the current collector or even went into the pores. So in this sense, a short circuit would be very bad. It destroys basically also the current collector.
But don't you think it's mainly because you use a foam?
Yeah, it's because of this foam, exactly. But on the other hand, the metal, what is on the bottom, these heavy metals, they are all extremely corrosive to other metals. So if you say on the top you have sodium, and maybe for sodium you could even use simple steel, since the steel should not get in contact with the bismuth, because bismuth is quite aggressive. Maybe this is only a theoretical problem. There, I'm unsure.
Oh, I think that you better know about practical problems than I do. So you're surely right that it's not so simple. But as you know, when you try to make theories, you need to make very academical hypotheses and assumptions, and voila, that's what I need to do. But in that sense, there's also that article, which is the self-healing battery of, I don't know exactly who's the first author of that, but it's the group of Sadway, who presented this problem of intermetallic phases appearing and said it appears, but they dissolve back again. So, and I think that in these experiments, was there a foam already? Probably yes.
But they need to stay always below of the electrolyte.
Mm-hmm.
If you have it attached to the current collector, if you get bismuth into the lithium phase, then you can never remove it again.
Mm-hmm.
It stays there forever.
Even when even when there would be no foam.
Yes. Tom, please correct me if I say something wrong.
Well, I don't know. I think that you better know.
I would never correct you, Norbert.
Was?
No, you're probably right. I don't know yet if it's the people that we spoke to, they were not very interested in this topic. It was chemists from our university, but they didn't seem very bothered by the idea that there would be a short circuit. So, well,
even if the bismuth, let's say, if we assume that the bismuth dissolves in the electrolyte a little bit, then it would go up and alloy into the lithium. But I would not know how to get it ever out of this lithium again. So it would simply dissolve there, stay there forever.
But lithium dissolves in the bismuth, but are you sure that the bismuth dissolves in the lithium?
Yes.
Okay.
They can simply mix.
At any ratio?
I'm not absolutely sure. I would need to look in the phase diagram. But the lithium can travel between both electrode sides, but the bismuth not, I would say. There we would get problems.
Well, I don't know. I already heard about these batteries that can exchange in both directions. You can have material moving from one side, from top layer to the bottom, and the inverse case is also possible, so that you can have double charge transport. Probably that exists, but I don't know how it. I'm really not familiar enough with that. We're on the fluid mechanics physical side, and we've been more and more surprised by what electrochemists are learning us, and I think that you've been on the same type of trajectory.
Probably you could even deposit the bismuth, but you would need another voltage, no, that it travels. And I have no idea how large this voltage is. We could check in the Tom, wie heißt denn das? Die Standardpotentiale, oder? The electrochemical. Oh, I would say at least if you have, for example, on the top lithium, magnesium, and sodium, you could move all three of them. But first you would move one of them, then the second, and everything depends on the standard potentials.
Right, yes.
And this is complex. And the thing is, when you apply voltages which are too high to the battery, then you dissolve also the electrodes. You get corrosion. So yeah, I don't know. Short circuits we should avoid. But does anyone of the audience know whether such short circuits due to sloshing already appeared in liquid metal batteries? Has someone any feeling?
Well, there are little people that make them. Huh? So I think that if you want the answer, so you can just take your liquid metal battery, Norbert, and put it on Gerrit's machine for orbital sloshing, and it will short circuit, and you will have the answer.
That's a possibility, yes. Maybe we should try it someday.
Yes.
But the sodium zinc battery, which Johan built, I understood from the others, also the presentation was very nice. I understood that it survived for only 2 hours. So this will be difficult to do nice experiments with that.
Well, you know, I think that you're really on the realistic side now of all this liquid metal battery stuff. This is, in some sense, it brings me back to the first one of the first slides. Which information is useful for the engineers that can make these batteries? I fear that not so much information of what we do is useful for the engineers that make them. But well, we've played this game of mapping out the different instabilities, and clearly for Hall reduction cells, this metal pad roll story was important. We can imagine that it is also important for possibly big liquid metal batteries, and that's the game we played. All the other the more relevant questions that you're dealing now with, how am I going to construct this system? I think it's really much more relevant, but personally, I'm not in. I don't have the experiment, the expertise to do that now.
There is nothing more practical than a good theory. Something. Several people said this already, among them Brandl from the German side and others as well. So I think it's very useful. In the end, if these cells will be built someday, the theory is already there. That's good.
Okay.
Well, yeah, thank you very much. More questions or comments, maybe? If not, I think we are on time to finish the seminar. I really would like to thank you. It's a very nice overview about instabilities.
Okay, well, it's my pleasure to speak before this international audience, I hope that we will be able to meet in live at some later occasion.
Sure, hopefully soon. Yeah, thank you very much again, and I will thank again the audience, all the colleagues. This is a transcontinental meeting, so have a nice afternoon, most of you, and good morning for some of us in this side of the planet. Okay. Guys.
See you, everybody.
Thank you.
Bye, Norbert.
Thank you very much.
Bye-bye.
Bye-bye. Bye-bye. Thank you. Bye.